Hello and welcome back to my calculus lecture series. Today we will be covering chapter number 4, Applications of Derivatives. We'll be covering sections 4.1 through 4.6, where we will be talking about extreme values of functions, the mean value theorem, connecting f prime and f double prime with the graph of f, modeling and optimization, linearization and Newton's model, as well as related rates. So starting off here with section 4.1, we will be talking about extreme values of functions. These will be both absolute extreme values and local extreme values, as well as how to find them. So let's talk first about absolute extreme values. So what an absolute extreme value is any value on a function that's either an absolute maximum or absolute minimum. So if we take a look here at figure 4.1, we see a parabola. We see y equals cosine of x, but it kind of looks like a parabola because we're only looking at it from negative pi over 2 to pi over 2. So the extreme value, the absolute maximum of this little function right here is going to be right there, right at the very highest point of the function. And you may have noticed that the other equation here, y equals sine of x, is actually the derivative of y equals cosine of x. In reality, it should be negative sine of x, but for this application, it's okay. So since it's the derivative, first up we will be talking about absolute extreme values. So an absolute extreme value is any value on a graph, on a function like we have here, that is either a maximum or minimum point, and it has to be a maximum or minimum point for the entire function. So if we take a look at this definition up here, we have absolute maximum value on D, and again D is the domain. In our case right here in figure 4.1, the domain would be negative pi over 2 to positive pi over 2. It's an absolute maximum value on a domain if and only if f of x is less than or equal to f at c, and c is going to be either a maximum, in this case it's going to be a maximum value. And we have a similar definition for the absolute minimum value. So an absolute minimum value on a function is where the function at some point c, where every other value of the function is greater than that. So in short, if we take a look at figure 1 right here, for this particular domain, for y equals cosine of x, our extreme value, our absolute extreme value, is located right here. Now you may be thinking to yourself, well, isn't y equals cosine of x a continuous function, like a continuous wave function? Well, actually it is, and that's why we have the domain here between between negative pi over 2 and pi over 2. Within this domain, y equals 1 is the absolute extreme value, and it's an absolute maximum. Now for our second function here, we have y equals sine of x. Now, take a look at the extreme values here. Since we only have it on the interval between negative pi over 2 and pi over 2, we actually have two absolute extreme values. We have an absolute minimum, which is right over here, and an absolute maximum, which is right over here. So let's move on. And we're just going to talk about absolute extreme values a little bit more. We have parabolas A, B, C, and D. Now, pay close attention to the domain, D right here. So for the first one, we have the domain as being from negative infinity to positive infinity. So as we approach negative or positive infinity, this parabola just keeps growing and growing. So we're never going to actually hit a maximum, an absolute maximum value. However, the vertex right here at the bottom is an absolute minimum, a global minimum value. So you'll hear absolute and global kind of used interchangeably here, but it just means overall for the entire graph. So let's move on here. 2b. Well, since we have a domain here of 0 to 2, then we have an absolute max and an absolute min. Again, we have an absolute minimum for this function at the vertex, and then we have an absolute maximum right up here at x equals 2, because that's the domain. So interesting there. So let's take a look at C. And now notice that the domain is from 0 to 2, but it does not include 0. Interesting. So that means that we only have an absolute maximum value, which is located up here. Now the fact that it doesn't include 0, you might think, well, don't we have can't we get just really close to 0 and still be, still have an absolute minimum? Well, the answer is actually no, because you can get infinitely close to 0, but you can't actually reach it. So we don't have an actual global minimum for parabola C. If we go to parabola D, we have a domain of 0 to 2 that doesn't include 0 or 2. And that's because we can approach 0 and we can approach 2, we can get infinitely close to it, but we can't actually hit those values, which means that there are no global minimums or maximums. And all of that is outlined in this table down here. Now let's continue with a few more examples. Please note that these are all on closed intervals, that all of these functions are on closed intervals. So let's take a look at this first one right here. We have some function y equals f of x, and we have a maximum and minimum at interior points. So we have a maximum right here and a minimum right here at interior points. That's very interesting. This next one over here, we have max and min points at the endpoints. So we have this maximum right here and this minimum right here. Here we have another variation. We have a global maximum at an interior point, that means within the bounds, and a maximum, we have a maximum at an interior point and a minimum at an endpoint, which is right over here. Next up, we have a minimum at an interior point and a maximum at the endpoint. Kind of the opposite of what we just had. And this is where we're going to get into the distinction between absolute and local minimums and maximums. So if we take a look at the graph on the bottom, here we have an absolute minimum. That means that's the lowest value, lowest y value on this plot. Next up, we have a local maximum right over here. That means this might not be the highest peak for the entire function. However, in the vicinity, it is the highest point. And same over here, we have a local minimum point. It's not the lowest value for the entire plot, but it is the lowest value within a certain increment here. Now, here again, we have an absolute maximum value, aka a global maximum value for this function, and another local minimum. So again, this absolute maximum is the highest, the largest y value that this function can attain, and right here we have the lowest y value that the function can attain. And in between we have a bunch of little peaks and valleys, or not a bunch, just a couple peaks and valleys, that are locally maximum and minimum points, but not absolutely, not for the entire function. And right here we have a definition for local extreme values. So let C be an interior point of the domain of a function f, then f of C is either a local maximum value at C if and only if f of x is less than or equal to f of c for all x's in some open interval containing C. And we have a very similar definition for the local minimum value. So again, if we take a look at our local maximums and local minimums here at the bottom, we have some interval. Doesn't really matter how big or how small it is. Actually, it does, but we can kind of toy around with how big or small the interval is here, as long as only one point in that closed interval is a maximum point, which appears to be right over here. And same thing for our local minimums. If we have some little closed interval here, then this point right here at that point is going to be our local minimum, because in the interval that I just drew here, let me actually draw that again, 1 second. In this interval right here, this spot is a local minimum. So the next thing right here is kind of important. We have theorem number 2 that talks about local extreme values. If a function f has a local maximum value or a local minimum value at an interior point C of its domain, and f prime, remembering that f prime is the derivative of the function f, and if f prime exists at C, then f prime of C is equal to 0. So what does that actually mean? Well, if we take a look at this figure number 4.4 here at the bottom, we notice that at the local maximum right here, we have a straight line that seems to be balancing on top of this maximum point. And that's actually the tangent line, which, as you recall, is the derivative of that function at that point. And it looks like the slope of that tangent line is 0, which would be in line with what this is saying right here. And what this is trying to communicate is that if we have a certain function like we have in this picture right here, and we take the derivative and find the derivative function, then at any point where the derivative function is equal to 0, we know that we have either a local or global maximum or minimum. That's because at that point, we're going to have some sort of tangent line. However, it's also important to note that that doesn't work both ways. For example, if we have an f prime of C that is equal to 0, we know we have some sort of local maximum or minimum. However, we can have an absolute maximum or absolute minimum, or local max or min, that is not differentiable. For example, the absolute minimum on this graph right here is not really differentiable, is it? Or right here, we can't really draw a tangent line at these points, so we can't find out what the global max or mins are, nor can we find out what one of the local minimums is for this graph. But if the function is differentiable at a certain point, and it has a local maximum or minimum at that point, then we know that when the derivative is equal to 0, we have a local maximum or local minimum. And in some cases, we have an absolute max or absolute min as well. It's just not in this function right here. So here we have our derivative plotter again, and we have a very basic function. F of x is equal to x squared. Now, as you might have guessed already, the absolute minimum point on this graph is going to be at the vertex right here. And if we go to x equals 0, we have y equals 0, which is the vertex of this parabola and also the global minimum. And notice what happens when the tangent line goes to the vertex. Right as we hit it right there. That's kind of hard to hit exactly, but you can sort of see what would happen. That tangent line would flatten out. There we go. That tangent line would flatten out and have a slope of 0. And if you look at the derivative function on the bottom, indeed we have y equals 0. So that is called, once again, a critical point. Anytime the derivative function, like we have on the bottom, hits 0, hits y equals 0, we have some sort of critical point on our original function. And that can be either a global minimum or maximum, or a local minimum or maximum. And this will have a lot of very useful applications later on. Next up, I want to do a quick example here for finding extrema values. So what we're going to try to do today is to find the absolute or local minimums and maximums of function g of t. And we're going to try to find those absolute or local minimums and maximums on the interval -4 to 2. So right here. And remember, since we're using square brackets, we're going to be including the values -4 and 2. So what do? Well, the first thing we have to do is take the derivative of function g of t. And that's going to look a little bit something like this. We differentiate it. And I'm not going to go through all the steps because this is a very simple derivative problem. But basically, g prime of t is equal to 6t squared plus 6t minus 12. Again, we use the power rule right here, and 4 goes away since it is a constant. So g prime of t is equal to 6t squared plus 6t minus 12. And so next up, actually one step before that, and in order to find out where g prime of t is going to be equal to 0, we want to factor it like we do right here. That way it's very easy to figure out where g prime of t equals 0. Which looks like it's going to be at t equals -2 and t equals +1. And if we graph this, we have the red curve right here is g of t. And this parabola right here, the blue parabola, is going to be g prime of t. Remember, prime is like the thing that looks like an apostrophe. So let's see. Well, here we have t equals -2 and t equals 1. So let's see what happens at t equals -2 and t equals 1. Remember, this is t right here, and this is going to be y right here. So at t equals -2, it looks like our blue derivative function is 0, which makes sense because we already kind of solved for that here on the left-hand side. Likewise, when t equals +1, we also have a 0 for our derivative function. And if we draw a line directly upwards from those points, or directly downwards, we see that we're hitting local maximums and local minimums. So, what happens there? Well, if we take the tangent line like that, then the slope of that tangent line and that tangent line, the slope, rise over run, is equal to 0, which makes perfect sense. That's where the derivative function equals 0. Now, we can't just stop there. We also have to evaluate first we have to evaluate where g prime of t is equal to 0, and we can't stop there. We have to also evaluate at the bounds. So that means we have to evaluate g of t at the bounds -4 and 2. So what we're going to have to do is we're going to have to plug in these two values into this equation right here. And we're also going to have to plug in the values t is equal to -2 and t is equal to 1. We have to plug those in into g of t and see which ones are going to be the largest or smallest values. So first we plug in -2 that we got right here. Then we're going to plug in 1. Then we're going to plug in -4. And we're going to plug in 2. So remember, we have -2 and 1, which are where g prime of t is equal to 0. And also we plugged in, for t, we plugged in -4 and +2, which are the bounds that we're evaluating all this over. And we'll take a look here. Well, g at -2 is equal to 24. And that's the highest number. And also g at -4 is equal to -28, which is the lowest number. So those are in fact going to be our extrema values. Those are what we're looking for, which makes sense because over the interval -4 to 2, this right here is the absolute largest value. This right here is the largest value, the global maximum for this function over the interval -4 to 2. And at t equals -4, which is way over down here somewhere, we have the absolute minimum. So if we're looking for the absolute max and min over this interval, we got it right here. At t equals -2, which is one place where the derivative function is equal to 0, and also at t equals -4, which is one of the bounds for this equation. And that just about wraps up section 4.1.